picking up in lesson 1.2, part 3. We were talking about even and odd. Brief synopsis. Even is symmetric across the y-axis, or f of x equals f of negative x. My suggestion is you try and find a happy medium of using the algebra, using the graph. Okay, I would not rely exclusively on one or the other. Odd has origin symmetry. You haven't seen that yet, but you're getting ready to. And then f of negative x equals negative f of x. Now, see in our awkward stopping point yesterday, we had found h of negative x, and we had an extra negative sign. So h of x did not equal h of negative x, and so at this point, all we know officially is it is not even, right? And so what is our next step that we're getting ready to do? We need to find, okay, that's going to bug me. I got to use the same blue. Okay, we need to find negative h of x now. Now, officially, negative h of x, if you recall, says you multiply, you distribute a negative. In this scenario, so we distribute a negative to each term, I would say. In this scenario, though, keep in mind, this whole thing is a fraction. So when we are distributing a negative, we're basically multiplying that fraction by a negative. So I'm going to show it like that, kind of like how I, showed the last one. We're going to take a negative, and we're going to multiply that function. Now, this is just one fraction, folks. When you take that fraction and you multiply by a negative, officially, it has 3 places it could go in my brain. It could go just out front of the fraction bar. It could go to the top of the fraction, and you distribute to the top of the fraction. Or it can go to the bottom of the fraction, and you can distribute through the bottom of the fraction. Based on the fact that I'm trying to see if this equals h of negative x, where would it make the most sense to put it? If we want it to look the same, it's going to go at the top, yes? Okay, and you could also just put it out front of the fraction, but what I'm trying to show you is that when multiplying a fraction by a negative, it goes top or bottom. It doesn't go both. Because if you multiply top and bottom by a negative, negative is a positive, you're multiplying by a positive. Okay, so at this point, we have the negative x cubed over 4 minus x squared. What did we just figure out? Okay, it's odd because we saw that h of negative x equals negative h of x, yes? So officially at this point, we can say it's odd. Okay? Now, I said use your calculator and graph in combination, yes? This is an important one to graph because do we totally understand what symmetric about the origin means?
Sure.
I'm going to go with no. So let's graph this. Or at least I can graph it and you can look at mine. X to the third over 4 minus x squared.
Take a road trip.
I don't even know why I'm putting it up here. You guys had it up there way before I did, right? Okay, your graph should look something like this, yes?
Yeah.
Okay, now, obviously, the algebraists told me this is symmetric about the origin. Okay, so symmetric about the origin. 1. I mean, can you see how the diagonal corners look alike? They have that, that's symmetric about the origin. Officially, I believe you could do a 180-degree rotation, and that would be equivalent to symmetric about the origin. Or what I also like to think is you can do a double reflection, and you can reflect it across both axes. And so, what I mean is, I kind of think, if I think in terms of, say, for instance, quadrant 1 here, this upper quadrant, and you just take that piece of the quadrant, and you flip it down, so now it's upside down here, so you flipped it across the x. Then if you flip it across the y, notice does it land on top of this other piece. And you can do the same thing with this upper left corner. If we flip it, say, across the y-axis, then it's up here. If you flip it down across the x-axis, it lands on top there. Does that give you a visual of what I mean by symmetric across the origin?
I think so.
Okay.
Just fold it in half and they're the same, basically.
Fold it in half and then also up and side down.
Yeah.
So the folding in half is the y-axis. The upside down is the x-axis reflection. So I like to think if I took that diagonal quadrant and rotated it about or reflected it twice, it would land on top of it. So. Okay, so officially symmetric. This is symmetric about the origin, or it has origin symmetry. Because officially it did ask to determine their symmetry. Okay, you got the basics on even and odd or neither. Okay, I don't remember what homework does. Don't expect homework to have a nice, neat one example of each, because it may. You can't count on that. That's a Mrs. Sargent thing because I want you to see an example of each. Okay, let's talk asymptotes. We've already talked asymptotes a little bit, haven't we? Okay, we've talked asymptotes a little bit already in 2. Officially here, we are talking about vertical asymptotes and horizontal asymptotes. Now, some key information. Vertical asymptotes. Places that make the denominator equal to 0. We've already looked at, like, when the denominator equals 0, how it's either a vertical asymptote or a hole, or in other words, non-removable or removable discontinuity. Okay, so vertical asymptotes make your denominator equal to 0. That's going to be key there. And to find them, you set your denominator equal to 0. Like, we want to know where it's going to equal 0. For a vertical asymptote, just like any vertical line, it's going to be x equals whatever that number is. Okay? And again, that can be found by putting your denominator equals 0. Horizontal asymptotes. Okay? We haven't reviewed this one as much yet, although I know I did mention it one day. So they're always y equals a number, because that's a horizontal line. And it depends on your powers. If the biggest power is on top, so if the biggest power is on top, notice there are no horizontal asymptotes. At some point, I think you end up seeing like a slant asymptote, because there usually is a slant asymptote instead of a horizontal asymptote, just goes at a diagonal. Okay, but there's no horizontal if the biggest power is on top. If the biggest power is on bottom, then y equals 0 is the horizontal asymptote. Okay, biggest power is on bottom. So if you look at your biggest powers and you have, say, x squared over x cubed. That's an example where bigger power is on bottom. You're going to have that horizontal asymptote y equals 0. I guess I didn't show. Biggest power on top would be what? That would be the idea of x cubed over x squared. I don't know if you really need that example or not, but there you go. Now, if powers match on top and bottom, take the coefficients of the largest powers. So, if coefficients match on top and bottom, or powers match. So, for instance, if I said y equals 3x cubed over 4x cubed plus 1. What do you notice about that example?
The powers match?
Powers match, yes. You have their x cubed and x cubed. So since the powers match, cubed and cubed, you use the coefficients. What do I mean coefficients? The numbers out front, the 3 and the 4. So that would be an example of a horizontal asymptote of y equals 3/4. Okay? We did that in algebra. I'm not saying you remember it, but we did do it in algebra. Okay? Okay. We're going to take this one big example here, and we're going to determine any vertical or horizontal asymptotes of the graph. Now, we're not going to go to the calculator yet. We can look at the calculator for verification in the end, but I want to talk about doing this without the calculator to verify. Okay, so any horizontal or vertical asymptotes? What would you like to start off doing here?
Set the denominator.
Okay, so setting the denominator equal to 0 is going to help me find my vertical asymptotes, yes? So my denominator is what? X squared minus x minus 2 equals 0. How do I solve that?
Factor.
Yep, that factors. Hey, if you get Algebra 2 kids asking for your help, they're going to be asking for factoring help. That's what I taught today. X squared breaks into x and x, multiplying to be -2 and adding to be
-1.
-1.
Plus 1.
+1 minus 2. Am I done?
No.
No. Now what?
Is that those equal to 0?
Set each factor equal to 0. So x plus 1 equals 0. X minus 2 equals 0. Solve those. X equals -1 or x equals 2. What are those? Those are my
Asymptotes.
vertical asymptotes. Okay? This is a scenario where there's going to be 2. Okay. Well, you got vertical out of the way. Now we've got to talk horizontal asymptotes. Okay, what do you notice about horizontal asymptotes?
Shape exceeds biggest power.
Okay, where is my biggest power? On bottom. So what is the largest power on top?
1.
X to the first, yes? So that's what, it's the only power, but that's what matters on top, yes? What is the biggest power on bottom?
2.
The rest of that stuff doesn't matter for horizontal asymptotes. That's all that matters. And so where is my bigger power? It is on bottom. So that means by default the answer is y equals 0.
I like that.
Okay? Now, again, we're not going to talk calculator quite yet. We're going to talk about the graph. Because I want you guys to see some things. Now, I'm going to kind of just squish this graph in because, you know, it is what it is. There's only so much room here, but we're going to make it work. I know I have a vertical asymptote at 2 and a vertical asymptote at -1, yes? So, a vertical asymptote at x equals -1 looks like what? Looks like that, right? A vertical asymptote at x equals 2 looks like that. What's a horizontal asymptote at y equals 0 look like?
DX.
Okay, it is the x-axis, right? Okay. Now, general rule of thumb here. Okay, you guys have worked with vertical asymptotes before. General rule of thumb is my graph does not cross or touch a vertical asymptote. Okay, that's the general rule of thumb. I don't have any exceptions off the top of my head. I'm not sure there are exceptions. Okay. Horizontal asymptotes are also what we talk about when we talk about end behavior, which is our next section. Horizontal asymptotes determine what's the graph doing at the ends. Okay. Now, can a graph cross a horizontal asymptote? Possibly. It just would have to be in the middle, not off on the ends. So as it starts going off to infinity and kind of settles out and it's done, you know, doing anything crazy, it's going to run along that horizontal asymptote. Now, because I'm the teacher and I know what I know, fair enough, not because I expect you to know this, okay? I know that because I have positive lead here, my graph would start up here on top of the horizontal asymptote, okay? Now, what's it going to do as it approaches that vertical asymptote? What's it going to be forced to do? It's going to be forced to go up, isn't it? So I know the first piece of my graph would look like this. And again, am I expecting you to know that off the top of your head? No. Okay? But I'm just trying to show you some connections, okay? Some of this is stuff we learned this year, you learn in calc, just. Now, a vertical asymptote, as long as it just had a single power, there wasn't like an x minus 2 squared, my graph changes sign. So right here, my graph was positive. Now my graph is going to be negative. So it's going to be coming from down below. My graph can do two things. Okay? It could hit that horizontal asymptote and go back down and do like an upside down parabola thing. Or because it's at the center, it could cross through there. And if we look at a y-intercept, that's the word I'm looking for. Okay? If we look at a y-intercept, you will find that it does cross at 0. And so this graph ends up crossing through at 0 and does something like that. And once it crosses through, it goes up. And this is not a perfect graph, but you get the idea. Now, I have a vertical asymptote again. General rule of thumb is my graph switches signs. So it's going to go from positive to negative, and guess what? It's going to be down here. What's it going to do is it hits that horizontal asymptote. It's going to run alongside of it. Okay? In behavior, this graph is going to approach 0 as it goes infinitely out left and right. Now, Brody, does my graph look like your calculator? Generally speaking?
Yeah.
Okay? So, I mean, by all means, yes, feel free to graph it on the calculator if you haven't already. But I'm just trying to show you that as you learn about this, there's stuff you know just by knowing your asymptotes. And that's kind of the idea of what I wanted to show. Okay. Vertical and horizontal asymptotes. You've got your rules, right? You're going to need to know those rules. Last year, I think I gave you a cheat sheet on the rules. You don't get a cheat sheet on your asymptote rules this year. Sorry. Sorry, not sorry. How's that? Okay. Okay, next. Okay, let's talk in behavior. Now, as I move on to in behavior, I talked about the horizontal asymptotes, right? In behavior and horizontal asymptotes, that concept overlaps. So we've kind of already talked a little bit about in behavior. For instance, what is my graph doing at the ends here? It's running along that y equals 0, yes. So it's going to approach, as it goes, heads to the high school office, as it heads to Mrs. Holman's room, it's going to get closer and closer to 0. How long can we hold the button down and still not be at 0 type thing? Okay? Now, so officially, in behavior is what is happening on the far left, so Mrs. Holman's room, far right, the high school office, right? Okay. What is the graph doing? When I say far left and far right, we can also think negative infinity and positive infinity. If there is a horizontal asymptote for the function, it will be approaching that number. And that's what I was just explaining in that last example. If the graph is going to infinity or negative infinity, then it will approach that value. And that's more the idea of like a slant asymptote, or just if there's no horizontal asymptotes, nothing. So let's look at each of these. It says to determine the end behavior. What I really want you to do, generally speaking, I need you to think horizontal asymptote. Okay? I need you to think horizontal asymptote. Now, as you look at that first one, y equals 3x over x squared plus 1. What is your brain thinking?
X squared plus 1.
The bigger powers on
Okay. My biggest power on top is the 3x. The biggest power on bottom is the x squared, yes? So rule of thumb there is that my bigger power is on bottom. Now, and another way to show this, what could you cancel if you're looking at just those? You could cancel a set of x's, and you have 3 over x. Okay, that's another way to kind of show this, because as you go off to infinity, a number 3 divided by a number that is getting bigger and bigger and bigger and bigger and bigger is going to make a fraction that gets closer and closer and closer to 0. Okay, but generally speaking, what was the key here? Bigger power was on bottom. Now, if you graph that real quick.
Yeah.
Does that agree?
Yeah.
And here's the deal. Do we have to graph asymptotes? No. Can it be helpful depending on the problem? Yes. Does that look like a horizontal asymptote of y equals 0? Yeah, I don't care what it does in the middle. End behavior. Okay? Let's look at B. What are you thinking on B?
The
But
powers are the same, so you take the
Okay.
number out in front.
We've got a 3x squared and an x squared. So powers, as stated, are the same. And you can think of it, if you will, that the x squareds will cancel, yes? So if you want to think of it like that, if the x squareds cancel, we have 3 over 1, which is just 3. Now, can you visualize what that looks like?
It goes up.
It's 3x squared over still x squared plus 1. Now, does that look like it maybe approaches 3 as it goes off to the side? And could you figure that out by doing some tracing action?
Yeah.
Possibly. However, it's, again, so much in this chapter I keep talking about, make the graph and the algebra work together, right? There's so much, I do not want you relying on just one over the other. Okay, what about this last deal?
Biggest power on top.
Biggest power is on top, yes? If we look at this, we are comparing 3x cubed over x squared. What's the rule when the biggest power is on top? Okay. Officially, now, that's, okay, I'm going to write no horizontal asymptotes. However, did they ask me about horizontal asymptotes officially in this section?
No.
Officially, they're asking me for end behavior. So, okay, there's no horizontal asymptote, but there's still something going on. Does that make sense? So, think about a canceling scenario. 3x cubed over x squared. What can I cancel here?
The X. You can get rid of 2 X's.
Okay, I can get rid of an x squared. What's that leave me with?
3X.
3x over 1, which is
3X.
3x. Folks, your end behavior follows along the line y equals 3x. What's the graph y equals 3x looks like? It's a line that has a slope of 3 and an intercept of 0. So let me, okay, I want you guys to see this real quick.
Oh my goodness.
3x to the third over again x squared plus 1. Now, here's just the graph. Maybe. Okay, that's the original graph. You see a diagonal bit happening. Okay, there's definitely a diagonal bit happening. The question is, what's my graph doing as it goes off left and right? Well, it's either going way up or way down. What did we just say that asymptote is?
3X.
Well, it's a slant asymptote. 3x. Watch how this graphs. Does the graph run along that diagonal line? It does, okay? So that would be the idea of a slant asymptote, but it's the end behavior. Because as my graph is going along those ends, it's getting closer and closer to that line there. Okay? Okay. So I didn't want to hold myself to it. I said yesterday if I could get work time, then I said I don't know how long this was going to take me, and yesterday threw me all off. So you do get some work time. Fair enough?
Yeah.
Okay. I think it's like 10 questions again.
Yeah.
So you're going to have a couple of each. I can't remember all what's in there, but please, please, please read the directions. Looks like you've got 4 even odd neithers. And you've got some various asymptotes and whatnot. Okay?
Okay.
Give it a try.